This is lecture 43. We're going to talk about the Itô stochastic integral. Okay, so remember what we did last time. So last time I gave you the general form for a stochastic differential equation. So it had this form dx is equal to alpha dt plus beta dw. So in general, I said the solution had this general form where you had the standard Riemann integral and then this Itô stochastic integral. So this Itô stochastic integral is what I'm going to just talk a little bit about today. So there's this whole field that has to do with Itô stochastic calculus. So think about how much you learned in your own calculus classes. And Itô stochastic calculus has its own big, broad area. So we're not going to cover all of Itô stochastic calculus, or even a small portion of it. What I do want to give you is a feel for it's not the same as the standard Riemann integral. So my hope for this is to give you a little bit of taste of Itô stochastic calculus, explain kind of what it is and why it's different just a little bit, and then go on into, so then the rest of the semester we'll actually look at deriving stochastic differential equations and numerically solving them. Okay, so there's two ways to define a stochastic integral. One is the one that we're going to actually be looking at is the Itô stochastic integral. And another one, I'm not exactly sure how you exactly say this name, but Stradinovich, I'm not good with these names, but stochastic integral. So the Itô stochastic integral refers to this Japanese mathematician who developed much of the basic theory. And then the Stradinovich stochastic integral actually is a Russian physicist who defined an alternative to the Itô stochastic integral, so another way of actually doing this. And they each lead to a different type of stochastic calculus. So we're going to use the Itô stochastic integral in this course, and it's really important that when you actually define stochastic differential equations, you define it as this is going to be an Itô stochastic differential equation. Because there's different calculus involved depending upon which type of stochastic calculus you're talking about. Okay, so a little bit of the terminology. So if we let x of t be a stochastic process, and we want to look at f of t, x of t, be some function of the random variable, and let's just denote f of t x of t as just f of t. Then the Itô stochastic interval is defined for random functions f such that the expected value of f squared is less than infinity on some interval a to b. So the way we can think about the Itô stochastic interval is to find the integral of a to b of some function with respect to w, remember our Joyner process, is equal to this. Here I have L dot I dot M dot. So this is a different type of limit than their typical limit, and I'll talk about that in just a second. But it's the limit as k goes to infinity of this summation. So this summation looks a lot like what you had for Riemann calculus. So Riemann calculus, your ordinary calculus, where here this delta w is just WTI plus 1 minus WTI, similar to the way we had delta t, it was Ti plus 1 minus Ti. Here A and B were thought to be an increasing sequence, and our change is just B minus A over K. And here this L dot I dot M actually means mean square convergence. So it's a little bit different than what we had before. So mean square convergence, what do we mean by that? We mean that if we have some function capital Fk defined according to this, and I is this integral of f of t dw, then what we mean by mean square convergence is the limit as k goes to infinity of the expected value of f of k minus I squared is equal to 0. So here we have the expected value involved. And so that's what we mean by mean square convergence. It converges in terms of the mean or expected value of this fk minus I squared. So a theorem here dealing with these Itô stochastic intervals. So assume you have f of t and g of t and two random functions in which the expected value is less than infinity for some a and b, and c is between a and b. Then here you have the integral of alpha f of t dw. You have the same idea that you can pull your constants outside of the integral. So this is the same as what we had for the Riemann integral. Similarly, if we have two functions that are adding together, so for this Itô integral, we can actually add the two integrals. And similarly, if we have a constant in between a and b, then we can split the integral up into two different integrals from a to c and then from c to b. So those are the same as what we had for the Riemann integral. Some other things that we have is we have the expected value of this integral from a to b is actually equal to 0. And the expected value of this integral squared is the same as looking at the integral of a to b at the expected value of f squared. So we can think about bringing this expected value in and the squared, and here we have this. Okay, this is what's called the Itô symmetry property. Okay, so without working throughout the details, and if you're interested in the details, you can see the book, and there's lots of other on this Itô stochastic calculus, and I really just want to give you the basics here. But without working through the details, it can be shown that here you have, if you have an integral of a to b of wt dw, so think about how we used to have like x dx, for instance. So this is w dw. Then this is going to be 1/2 w squared minus w squared of b minus w squared of a minus 1/2 of b minus a. So think about if this were x dx, right? So if this were x dx, then we would have had x squared over 2, and we would have evaluated it from a to b. So we would have basically had 1/2 b squared minus a squared. We would not have this extra part over here. And in general, for a Riemann integral, if we had f of x df of x, then we could write this as 1/2 f of x squared, which would be, and this should be f of b minus f of a squared. Sorry about that. This should be f of b squared minus f of a squared. So in general, what we have, if you look at an example here, so this example is, this is our f of x, this is our whole df of x, right? So this is our f, and then our derivative of it is 2x plus 3 dx. We can actually write this as the integral of u du, just by doing u substitution. Integrate, plug back in what your u is, and then you have 1/2 f squared of b minus f squared of a, which is what should have been here as well. Sorry about that. Okay, so stochastic differential equations have this form, so this is a special case in which we say alpha is just alpha of x doesn't depend upon t, and beta is 1. So assume that we have this form. So then what stochastic differential equations does a function of x satisfy? So basically what we're saying here is assume x satisfies this differential equation, this stochastic differential equation. Then what stochastic differential equation does some function of x satisfy? So if we think about the chain rule, so remember you have u of x here. So you can think about, normally if you use the chain rule, you have u prime of x times dx. So this is normally the chain rule from calculus 1. So here, remember dx, if we just plug this in, then this would be what our typical chain rule would give us. The typical chain rule does not apply for Itô stochastic differential equations though. So in general, if x of t is a solution here to this Itô stochastic differential equation, and we want to think about some function, and we're going to think about the function of x here. So if we have f of xt is some real value function on a and b, and we know the partial derivatives exist, then Itô's formula tells us that the differential equation for f of x is this little f dt plus this little g dw, where the little f is defined to be the partial with respect to t, plus alpha times the partial with respect to x, plus 1/2 beta squared times the second partial with respect to x. And our g is just our beta partial of f with respect to x. So for example, we're going to use Itô's formula to actually verify that that formula I gave you earlier. So here, if we let f of tx be x squared, then if we look at the different partials, the partial with respect to t is just 0, with respect to x we have 2x, and with respect to the second partial with respect to x is just 2. And we assume that x of t is w of t, then dx is just dw. So this is a SDE with alpha equals 0 and beta equals 1 here. So then using our formulas, what we have is the partial of f, in other words the partial of w squared, because our f is x squared, is just little f plus dt plus little g dw. Here our f is our partial of f with respect to t, which is just 0. Our alpha is 0. 1/2 our beta squared, so here our beta is 1. And the second partial of f with respect to x, which is just 2, so this just gives us f is 1. And our g of tx is just our beta, which is 1, and the partial of f with respect to x, which is 2x here. So what we get, putting this all together, so this is what we had before in the previous slide, then this just gives us that the derivative of w squared is our 1, our f dt, plus our 2w dw, or we can actually solve for this wt dw, and we have this part. So remember, I'm deriving that formula for the integral of wt dw. So we take that and integrate it. We integrate this from, we integrate the left hand side and the right hand side, and then we just end up getting this 1/2. The derivative of w squared is just w squared of b minus w squared of a, minus this typical integral 1/2 b minus a. So that's the same formula that we had previously. Okay, so just a quick side note, if you actually have the stochastic differential equation, then the PDF for the solution for our random variable x, the solution for it satisfies this former, partial differential equation here. Okay, so what we're actually going to cover is there's a lot of stochastic differential equations that can't be solved analytically, and to solve things analytically we need to go into a lot more detail about Itô calculus. I just gave you a broad overview just to show you that it was different than the Riemann calculus. We don't have time to go into that in this course, and so what we're going to focus on is the majority of those stochastic differential equations that can't be solved analytically, in which we would actually find numerical solutions for. So what we're going to do next time is we're going to actually derive a stochastic differential equation using a continuous time Markov chain. And then we'll do that for a couple of lectures, talk about a couple different, and then we'll actually go on and do a numerical implementation.